So good morning, good afternoon, good evening, wherever you are. And Tara actually had a slide with the Golden Age of SAR. It was almost like we'd planned this, but this is kind of my theme in terms of, I think we're just about to enter it. Okay, I've been around working with synthetic aperture radar for some years now, I guess maybe 30 years. So it has been remarkable to see the transition that we are going through. And just to mention, I've got one foot in academia at the University of Edinburgh and 1 foot in business and in the commercial world in Earth blocks. So I'll try to give a perspective from both of those sides. So are we entering a golden age of SAR? I would argue very much that we are. I remember, in fact, the very first images coming out of the ERS-1 satellite back in the 90s. We'd had some activity in terms of space, but not a regular, consistent synthetic aperture radar images. All through the 90s, it was fantastic. Even a bit of interferometry thrown in, that was great. By the mid-90s, we even had RadarSat, so first commercial radar operator. And everybody got really excited, and everybody talks about how you don't have to worry about clouds and you can see at nighttime. But all through the 90s and the early 2000s, I used to show this cartoon. It's a cartoon by a cartoonist called B. Kleban, who I recommend you go and search out. And it says the first electric shoes often attain speeds of 7 miles per hour, 10.2 kilometers per hour. And I always saw synthetic aperture radar is really being a bit like electric shoes, is that it was a very cumbersome bit of technology, very difficult to operate, quite complicated, and really did something that we were already quite capable of doing. So walking. And I think for a long time we kind of suffered in synthetic aperture radar, is that is pretty much how people saw it, is that everybody would get excited because you could see through clouds, but we lacked any systems with significant polarimetry. We lacked the consistent repeated measurements that we needed to do, regular monitoring, the kind of information, the multi-spectral information that you get in optical domain, we weren't really capturing in multi-frequency. So, but then when we got into this century, it suddenly occurred to me that, well, electric shoes, we kind of have entered an era of electric shoes where there's quite a lot of electric devices now. Technology has moved on so that we now have the equivalent of electric shoes. And I think that's where we're moving to now in the context of synthetic aperture radar, is that the technology has moved sufficiently far on that we are really entering a time where it is very exciting for synthetic aperture radar. Now I realize that this slide is, I need to update this slide. I've not got Synspective in here or Space Alpha. I don't have Umbra in here, in fact. And a serious emission actually is Pulsar, I should have in there also. But it gives you an idea of, somebody was asking in the chat about how many SAR satellites there are. There's a lot of SAR satellites, but a lot of these are constellations, and a lot of them, and Synspective, you know, is an example of that, of launching multiple satellites so that you get repeated measurements. And I think that's a significant thing. So the key thing about Sentinel-1, I would say, and why it is exciting, is that from about 2015 onwards, we have very regular, almost global land surface measurements. So in some places of the world, you're getting them virtually weekly. And it's that, and because of the lack of cloud cover, it is absolutely weekly. So somebody asked in the chat about how it can, you know, SAR compares, or the fact that SAR data often doesn't compare well with multispectral data when doing things like crop classification. Well, I would argue as well, if you're doing that with one scene and it's one particular day and you happen to have got your cloud-free day, then that's quite possibly true. But if you've got a long time series of weekly measurements over your crops, I would say SAR data is probably going to work pretty well. Depends on how cloudy the place you live in. I live in Scotland, so you know, SAR data is a particular advantage for us up here because it's very often cloudy. So Sentinel-1 has changed the game, I think, because it's freely open data, and it is regular and global. It is definitely the case. It's still difficult to use. So Antara mentioned the fact that you can get analysis ready data images of Sentinel-1 on things like Earth Engine, but we're not quite there in terms of getting all the information that we can extract out. So coherence, magnitude. I have a research student, a data science research student at the moment, actually looking at multiple combinations of Sentinel-1 data to look at interferometric coherence and magnitude. So she's looking at annual data. So that's about 1,000 pairs of coherence images for each pixel, and trying to use machine learning techniques to extract out what the patterns and clusters in that, because it's very difficult to extract out clusters from and patterns from that level of data. But the other exciting thing is the commercial players. So Capella, ICEYE, Umbra, now Synspective in Space Alpha as well. I'm going to show some examples from Capella and Umbra later. But they've changed the game because of the repeat frequency, the way that you can go online, virtually online, and you can take out your credit card and you can task a synthetic aperture radar image, and you can get that very quickly within about 24 hours now. That's significant. That's a game changer as well. Very much driven by military applications at the moment. I think that's certainly companies like Capella. I think that's what keeps their lights on. But then we've got other things. So NISAR and Biomass, they're going to be amazing once they're launched. They should be launching in 2024. So I think the most recent date I saw for NISAR was January 2024, so very soon. So that's the NASA and Indian Space Agency combination for an L-band system. That is going to generate so much data. It's going to be incredible, and a very high quality L-band data. I think the statistic is it's going to generate about 50 petabytes of data every year. And so over a 3-year predicted mission lifespan, that's 150 petabytes of data. To put that into context, Earth Engine contains around about, I think it's about 60 or 70 petabytes of data. So it's a huge resource, and it's the Alaska Satellite Facility that has got the job of managing that data. The Biomass mission from ESA, that is going to be a remarkable mission as well. That is the first time we're going to have P-band, so very long wavelength synthetic aperture radar in space. Polarimetric, having capacity to do very sensitive measurements of forest biomass, hence its name, but also being able to do things like tomography, sorry. So SAR tomography, so 3-dimensional structure information through the canopy of the densest forests in South America and the rest of the tropics. So that is going to be a significant advance. And then Tandem L is an exciting concept. So that's an L-band system that's going to fly 2 satellites in parallel. So a bit like the Tandem X with the TerraSAR-X satellites. And that's going to fill in a lot of the gaps that the Biomass mission might otherwise not be able to do. So that's the future in terms of where we're headed. The number of SAR satellites in space just now is nothing compared to what we're going to have in about 5 years' time. It's going to be very, very, very busy in terms of the electromagnetic spectrum. And that's going to be my last slide today in talking about the electromagnetic spectrum. Now, I'm going to give you a couple of examples here from the very high resolution imagery and what you can do. This is a storm that hit Scotland, Storm Arwen, in November 2021. It had a huge impact on the forest resources in Scotland. Forestry is a big industry in Scotland, and it was some crazy statistic like of all the amount of timber that would be harvested in a single year. This storm blew down about 20% of that in one night. And so it is really important to be able to recover and identify where the wind damage has been a very quick response. So in the combination with the University and Blox, we contacted Capella, and they very kindly, out of research interests, collected this data. And what you can see, if you can zoom in, that kind of, it looks like the land has been combed with a hair comb or something. That's actually all the stems of the trees having blown down. So on the left-hand side is still upright forest, but that area that looks like it's lots of threads is actually all the trees having blown down. And so and over that larger area, you can see there's a number of regions where you could map in high detail where these trees have been blown down. And this is really important from a management perspective, because then you can manage the recovery of all this timber. Another example, recently, if you've been following the news, there was a lot of flooding in the Southeast Africa. I do a lot of work in Malawi. I've got a number of former students who work there, including somebody, Alice Guedeza, who's the assistant surveyor general in Malawi. And they always have difficulty accessing high resolution imagery when there's a big flood in Malawi. Often in March time, they'll be flooding, but this year it was very significant. I think it was over 200 people had died as a consequence. So we contacted Capella and Umbra to see if they could collect some data for us, which they very kindly did, simply as a humanitarian response thing. And this is an example of a Capella image. On the left is the optical image just from Google Earth. On the right-hand side is the SAR image. And what you can see, so Antara talked about the being able to see surface water because it's darker in this radar image. So all this dark area here basically cuts across this road. So my hand-drawn yellow arrow here is the line of the main road going through that village. And you can see that the flooding has actually completely washed away this road. And so this data, it's about 1 meter spatial resolution after it's been multi-looked. So that was a question that came up about the resolution of synthetic aperture radar data. Always be careful to check the number of looks, because that has an impact on the quality of the image that you will see. But this isn't just an example of that rapid response and the fact that you're guaranteed an image because it's cloud free and it doesn't matter what time of the day or night you measure it. So you can get a quick response and feed into the disaster response very quickly. This is an example from Umbra. So I don't know if any of you have been following Umbra and their very new and interesting data policy. And it's very much worthwhile checking out. So they're another commercial synthetic aperture radar company. Any of you who have tried to or have handled commercial satellite data ever of any kind, well, or you should know, is that you're not actually buying the data. You're buying a license to use the data. And the use of that data has very strict constraints in terms of what you can or can't do with it. You can't resell it on. You can't share it with other people outside of your project. So they can be very restrictive sometimes in terms of what your license agreement is with the data provider. Umbra have actually decided to distribute their data on a Creative Commons 4.0 license, which essentially means when you buy the data, it's entirely yours. If you want to put it on a website and give it away to everybody, you can do that. If you want to derive products, you can do that. If you want to make a poster out of it or make a t-shirt, you can do that. So you can do anything you want on the data once you've bought it because you own it. And that's a significant change, I think, in terms of what we'll see of how it'll be interesting to see if they influence the other data providers in making the provision and access to data a little bit more open. But I chose this example. This is actually from Shetland in the north of Scotland. It was collected by Umbra, and this is from their open data set. So they have a freely available open data set. You can go and experiment and explore. And some of them, like this scene here, actually has a sequence of images over time, so you can see things changing. But these circles here are large gas storage tanks. And one of the things that synthetic aperture radar has been used for successfully is actually monitoring the tanks as they increase and decrease as they're filled up or emptied. And that's in terms of supply chain and energy management, that's a significant piece of business intel. Now, the other thing that's been mentioned is interferometry. Now, I show this diagram. This is 20 years old. It's still a fantastic image. I used it in my book, so I know how old it is. TRE created this long time ago with ERS data. It's not even Sentinel-1 data. And this is London. So, in fact, just about where that white triangle is where all the shenanigans that were going on Saturday at the coronation. If anybody was watching that, it was just about there. But this is the Thames. And what you can see is that there are displacements here. So subsidence or rising as geographical features throughout the city. So it's not just noise, it's clearly geographic. But what's amazing about this figure is that the scale bar goes from -4 millimeters per year to +4 millimeters a year. So it's only the entire variation across the whole of the city of London is only like that's that sort of distance. But it's taken a long time to actually turn this into, very serious business opportunities. But we are now in a scenario, TRE continue to do that. I put a link in the chat to the European Ground Motion Service, for example, which does this across Europe. on a regular basis. And there are also now companies like SatSense. SatSense is based in Leeds, and they do, as a commercial company, interferometric based services. So in this case, they're looking at ground motion and risk, the railway line that goes along here at the coast. So this is one of the studies. You can find that on their website. So we are now in a scenario where there are commercial companies providing commercial services on a regular basis based on, in this case, interferometric data from synthetic aperture radar. So we are now in a world where this is consistently happening. Now, the other thing that came up was in the chat was the lack of experts and the difficulty that we have with handling synthetic aperture radar data. And that's one of the reasons that I got involved in Blox, is because we're trying very hard to make the access to that data much easier. Now, the analysis ready data for Sentinel-1 is only the GRD data, so it's only the intensity information. There's no phase information there. But I believe Google are changing that, and they hopefully sometime this year will start introducing interferometric coherence magnitude as one of the data layers on Earth Engine. So I'm looking forward to that happening, and that's going to bring in an extra layer of extremely interesting information, especially for change detection, that we'll be able to use simply in the context of products like Blox or other things. But Blox, that's what I'm interested in terms of making it easier to access this kind of data. The idea, just very quickly, if you go to the link, you'll see a small animation on the website. But the idea is that Blox is based on a visual programming interface. You drag and drop the blocks to do the instructions. We've got Pulsar data and Sentinel-1 data. The entire archive is available to analyze in there. Now, the thing I'm going to finish on is talking about the electromagnetic spectrum. The electromagnetic spectrum is one of our limited natural resources, which is often forgot about. And this is a Sentinel-1 image of the English Channel. It's taken over a long time and taken the maximum. So you can see the shipping lanes here. You can see the offshore wind farms. But this pattern down on the left-hand side, that's radio frequency interference. And that comes from a number of different areas. Because if you look at the electromagnetic spectrum, in the microwave region down in the gray boxes on the left, is that lots of other people are trying to use that part of the spectrum as well, including our devices like telephones. It includes military radar installations. It includes lots of different types of transmissions that everybody is trying to access in here. And the challenge is that will increasingly impact on our ability to use synthetic aperture radar from space if we don't actually manage and control the electromagnetic spectrum effectively and make sure that Earth observation is a key component in there, and that the telephone companies don't just push us all out the way and say, well, we're not important enough. The other challenge we're going to have, based on how many satellites we see are going up into space, is that you also get interference from other SAR satellites. So individual SAR satellites can actually cause interference in other SAR satellites. And that's something that we'll have to watch out for in the future as we get more and more crowded in space. And on that note, I will finish. Thanks for your attention.